Hi, good day. I want to try and do this very quickly without going into details. We have a wooden trolley here. It's moving at 5 meters per second to the left, and then a bullet is fired here. And you see the speed of the bullet is VI. And then after collision, they move off together, right? With a velocity VF. We don't know VI, we don't know VF. We have been given the net force, F net force on the trolley due to the bullet, right? And we are to determine the initial velocity of the bullet. The trolley is initially moving to the west at 5 meters per second, right? Normally, what comes to mind when you see after collision that the two objects are together, you think of applying the law of conservation of linear momentum. Where you have to say after collision, the two masses are combined, become m1 plus m2 in brackets, all in brackets, times the final velocity. But in this case, you will notice that you are given the average velocity, average net force on the average net force on the average net force on the trolley. Yeah, given the average net force on the trolley. And the contact time, which is 0.02 seconds. So, right, what we are going to do, because we are given the net force, we are going to apply this equation here, which is the Newton's second law, the F net is equal to the rate of change of momentum. Right, let me see if I can do that quickly. So, this will be F net doesn't write very well. F net equals to delta P over delta T. So, which means you can equally use F net, the impulse formula, which is F net delta T there. F net times delta T is equal to change in momentum. Delta P, right? Which is your change in momentum is MVF minus MVI, right? But when we are using this equation, we're not doing it for both the objects at the same time. We take one object at a time, right? What is important for us to be able to do this one must note that if the average force, net force on the trolley is 600, by Newton's third law, the average net force on the bullet, the average force of the trolley on the bullet will be minus 600, according to Newton's third law. So, and then now we need to identify which objects to work with first to get this VF first, so that we can eventually find VI. Because there's no way we can find VI without knowing the VF. So there's some information we know the initial velocity of the trolley. We don't know the initial velocity of the bullet. So the best thing is to start this with, you put 600, we work with the trolley. So that will be 600 F net times the contact time, which is 0.02 there, comma 0, there's a comma here, comma 02. Yeah, it won't be very clear there, comma 02, 0.02, close bracket is equal to, we know the mass of the trolley is 5 kgs, 5m into VF minus VI into VF for the trolley. VF minus, hey, I forgot to buckle up here. Take to the right as positive. Your 7 belts are very important here. If you don't do that, you take to the right as positive. So the force, even the net force here was to the right. The force on the trolley due to the bullet, yes, is plus, okay? And then this is VF minus the velocity, initial velocity of the trolley is also negative. So that becomes plus, minus, minus. So that becomes plus, so plus 5, right? Then you close that. So which means this equation can give us the final velocity of the trolley. Very good. Now, once we find that velocity of the final velocity of the trolley is also the final velocity of the bullet, then you can use the same equation again, the same equation with the bullet. The mass of the bullet is 0.05. The final velocity, we would have calculated it. Then the initial velocity, you just call it VI, so it will be minus, change in momentum will be M into bracket, same approach, and then you'll find the initial velocity of the bullet. I hope that, I hope everyone's following. That is it. I hope it's clear enough. Thank you. Yeah. Let's end this one.